Hello, and welcome to my Assessment Task 2, Design and Constructing a Curriculum-Led Response to a Design Brief. The first stage we're going to look at is the investigation and defining stage. The design brief. Firstly, we needed a client who is a family friend who owns and operates a farm in rural Victoria. The purpose, the client would like an aquaponics system installed to trial growing their own food, including vegetables and fish. If this system proves successful, they may expand it to use it to grow food for farm animals. Materials. My client would like to use materials from their farm to help reduce the cost of their initial setup. Continuing my design brief, there are some constraints. The main constraint for this build is that we're using existing materials and having a limited budget of $250. The design is a single loop aquaponics system where water is pumped from a fish tank to a grow bed and then returned, creating a continuous cycle. This system will be successful if it can grow produce and show that aquaponics is a viable option for future expansion on their farm. Existing technologies. In a world of aquaponics, there are multiple systems out there, including media bed systems, nutrient film technique systems, and deep water culture systems. The media bed systems are simple and effective, using gravel or clay media to support plant growth and filtration. Nutrient fill technique and deep water culture systems are more complex and require consistent water flow and additional filtration. For this project, I have gone with a media bed system as it is more suitable for a low budget build using existing farm materials. Compared to the other systems, the media bed requires less precise control and is more suitable for an outdoor farm condition and is easier to maintain and more forgiving for beginners compared to the other systems. The possible solutions. There's several design options that were considered for this aquaponics system. One was a vertical system which saves space but requires more complex construction and consistent water pressure. Another option was a multi-tank system which increases production but would exceed the budget and available materials. The chosen solution is a single loop system with one fish tank and one grow bed. This design was selected because it is cost-effective, easy to construct using available materials, and suitable for a trial system on the farm. Some of the materials from the farm that we are going to use is a 1500 litre water tank, which will be used as a fish tank, the IBC container, which can be cut to use as a grow bed. Materials that we will need to purchase will be clay pebbles or gravel that will be used for the growing media because they provide good filtration and support plant roots, a submergible water pump that will be used to circulate the water through the system, PVC and fittings. I'm going to move into generating and designing. Design number 1 is quite a simple design. The water tank and IBC tank are being used in each of the 3 designs. As you can see, the water tank is standing next to the IBC container which has been cut. The submergible pump feeds into an accessible filter and then up the far side of the grow tank. A bell siphon is used which uses gravity to help return the water. Design number 2 is very similar setup, but a major difference is the water tank being dug into the ground. The idea behind this is to lower the height of the overall tank. The pump runs along the inside of the water tank with an inline filter into the grow tank. A bell siphon is situated in the middle of the tank, with the return line running along the ground back to the tank. Design 3 is somewhat a combination of the 2 designs, keeping the idea of the dug-in water tank with the pump pumping into an accessible filter. It then runs along and comes up the top of the IBC tank. The bell siphon is to the side and is also coming above the water level of the tank, which helps aerating of the water within the tank. Another change in this design is the fact that I'm using 45-degree angles for the supply line, as I have learnt that this will help the flow of the water and the pump will not have to work as hard. Conclusion. Design 1 was simple but required more space and height, making it a little bit less practical. Design 2 reduced the system height by placing the tank in the ground, however increased construction complexity and required a bit of excavation. Design 3 was selected as it best meets the design brief, as it is cost-effective, practical, easy to construct using available materials, and provides efficient water flow through the system. As a result, my client picked design number 3. Evaluation. The success of this aquaponics project was based on the key criteria including cost, practicality, ease of construction, sustainability, and efficiency. These ensure the system met the client's needs while using available materials. Design 3 was chosen as the final solution because it best met the criteria. It was cost-effective and used existing IBC tanks in a water tank, and is simple to build. The use of gravity and 45-degree angle for the pipes improves water flow, which makes the system more reliable. Sustainability was a big part of the design. The system reuses water in a closed loop, reducing waste and supporting sustainable food production. Using existing materials also reduces environmental impact. Overall, the final design is functional, efficient, and sustainable. It meets the design criteria and client needs, with possible improvement being the addition of more grow beds to increase production. Here is my risk assessment. Electrical hazards can be mitigated by using weatherproof outdoor power points, RCD or safety switches, or keeping cables off the ground. Cutting of the IBC tank can be mitigated by using safety goggles, gloves, using correct tools, and asking for assistance. Heavy lifting, use appropriate lifting techniques or ask for help if needed. Here is a continued part of my risk assessment. Water spills. Make sure your area is nice and clean and potentially use non-slip mats if possible. Poor water quality. Regular tests and keeping a clean filter will help with this. Digging of the hole. Mark out the secure area and do not leave unattended. Here I have broken each part of the science, technology, engineering and maths components of a part of this aquaponics project. Overall, this project demonstrates how all areas of STEM work together to create functional and sustainable aquaponics systems. Here are my references. Thank you for watching my assessment task 2.